everyone, we're going to continue with the 2018 physics exam. We're doing section B now. Just make sure you read the instructions in the box. This one's probably the most important one here. And if a question requires more than 1 mark, you must show your working. Okay, don't just put an answer, put all the working that you can, just in case the examiner is not too sure how you arrived at your answer. Okay, because you're being marked on your communication as well, rather than just your ability to find an answer. Okay. Also, just make sure if the box has a unit in it, give your answer in that unit. And also another thing that's nice to remember is even if you put an answer in the box, make sure you also write it somewhere else on the lines, because if you do a transcription error, at least the examiner's got like a backup answer to look at. And then if all the working out is correct, then they'll award you the full marks. They'll just know that you did a transcription error. Alright, question 1. An electric field accelerates a proton between 2 plates. The proton exits into a region of uniform magnetic field at right angles to its path, directed out of the page as shown in figure 1. So that's what's going on here. There's a bunch of data here. Let's read the question. So part A, calculate the strength of the electric field between the plates. Alright, so here's a good place to actually talk about something that often gets overlooked. If you don't know where to start in a question, sometimes looking at the units in the box gives you a hint of what you need to do. So the units here is volts per meter. So it means you're going to be dividing a voltage by a distance. Okay, at the very least, that's something that you could work with. Okay, turns out that we've got a formula for this. So the electric field between 2 parallel plates, funnily enough, is the voltage between the plates divided by their separation distance. So going back up to our picture, their voltage is 10,000 volts, 10 kilovolts. So that's 10,000. And they are separated by 20 centimeters. Double check. Yep, 20 centimeters. 0.2 meters. Okay, 10,000 divided by 0.2. I'm pretty sure it's 50,000. Let's double check. 10,000 divided by 0.2, 50,000. Okay. Done. Okay. The examiner's report. Let's have a look at that. Let me bring it over here. Alright. Don't want to look at the answers for the next one. Alright. The most common error was to incorrectly convert 10 kilovolts to 10,000 volts. Maybe you guys just used the 10. I don't know. Okay, but most people got that right. Cool. Right, part B. Calculate the speed of the proton as it exits the electric field. Show your working. Okay, so what's going on is you've got a proton being accelerated across this potential difference. Okay, when a charge enters an electric field, the electric field applies a force on the charge, causing it to move, right? In this case, it's causing the proton to accelerate across. So by the time it gets to the end, it has gained some speed, okay? Now, it doesn't say that there's any sort of initial speed of the proton. So we can assume it starts at rest here. So that means we're just working out its increase in kinetic energy. And then from that kinetic energy, we can look at the speed. Okay, so how do we do that? Well, the force, actually, no, I'm not going to use that. I'm going to use the energy formula. So the work done on a charge when it's in a potential difference, a voltage, that's equal to QV, where Q is the magnitude of the charge. So in this case, it's 1.6 times 10 to the negative 19, that's the charge of a proton, and the voltage is 10,000. Okay. Now this is also equal to how much kinetic energy, in this case, it gains. Okay, work done is just change in energy, right? But in this case, that energy is increasing, and it's gained kinetic energy. So that's equal to half mv squared. Alright? And so V, just solving for V now, that's going to be 2 times all of this, divided by the mass, and then square root all of that. So 2 times 1.6 times 10 to the negative 19 times 10,000 over the mass of the proton. Double check what that is. Mass of proton 1.7 times 10 to the negative 27. And what's that equal to? Calculator time. Alright, so square root and a fraction. So 2 times 1.6 times 10 to the negative 19 times 10,000 over 1.7 times 10 to the negative 27. So I get this. Let's do engineering. 1.37 times 10 to the 6. 1.37 times 10 to the 6. Okay. Let's double check our exam report. There you go, there's the setup. Okay, QV, work done on a charge by a voltage, and that's equal to the increase in its kinetic energy. So subbing everything in, we get 1.4 times 10 to the 6. Easy. The most common error was to use a different formula. So apparently someone's used this one. This has got the magnetic field in it. We're not talking about the magnetic field yet. We're saying when it exits the electric field. Yeah. So that's that. Alright, let's do part C. With a different accelerating voltage, the proton exits the electric field at a different speed, now of 1 times 10 to the 6. Calculate the radius of the path of this proton in the magnetic field. Okay, so what's going to happen is, go back up to the picture. Okay, when a moving charge enters a magnetic field at right angles, it has a force applied on it that's at right angles to both the magnetic field and the velocity. Okay, so all three things, magnetic field, velocity, and force, they're all perpendicular to one another. Alright, with a different, yeah, we've already said that, calculate the radius of the path. Okay, so here we're just going to use our formula, so let's go to your formula sheet, this one. And we have a formula for when a charge enters a magnetic field and what the radius of that circular path is going to be. There you go, it's just that one there, R equals mv over qb. So that's all we're doing, mv over qb. M is the mass of the proton, which was 1.7 times 10 to the negative 27. Velocity is this new one here, so 1 times 10 to the 6 over the charge, which is 1.6 times 10 to the negative 19 coulombs, and the magnetic field strength was 2 times 10 to the negative 2 Tesla. Okay, calculator time. Where's my calculator? Here it is. Okay, fraction 1.7 times 10 to the negative 27 times, let's do 1e6. That's over 1.6 times 10 to the negative 19 times 2 times 10 to the negative 2. Looks good. 0.53. 0.53. Let's double check our exam report. 0.53. Let's have a read what they said. So while many students use the correct formula, they subsequently made substitution errors, including using the mass of an electron rather than that of the proton, having the wrong indices for the values for their charge. The question stated that students were to show their working, so the small number of students who did not show sufficient working could be awarded only partial marks. That's the 5% there. So show your working, okay, because it says show your working. Alright, just do what the question says. Right? Don't be stupid. Alright, question 2. A square loop of wire of 10 turns with a cross-sectional area of that passes at a constant speed into, through, and out of a magnetic field of magnitude that, as shown in figure 2. The loop takes 0.5 seconds to go from position X to position Y. So this loop of wire is heading towards the magnetic field in between these magnets, and it takes 0.5 seconds to go from like just outside of the field to just completely in the field. Part A, calculate the average EMF induced in the loop as it passes from just outside the field, position X, to just inside the magnetic field, show you working. Alright, so the average EMF, boom, we've got a formula for this. Okay, average EMF is equal to, technically negative N, don't worry about the negative, we're asking about magnitude here, times the change in flux over the time it takes for that flux to change. Now in this case we have, is it one loop, square loop? No, it's 10 turns, so that's your N. Okay, there's our area, this is magnetic field strength, and this is our time. Okay, now the change in flux, well, it goes from zero flux to full flux, and the flux is calculated by field strength times area. So putting it all together we get 10 times, that's our N, the area and the field strength. So 2 times 10 to the negative 2 for our field strength. So this is B times A. So 2 times 10 to the negative 2. And the area of the loop is 1.6 times 10 to the negative 3. And all of that is over 0.5 seconds because that's how long it takes. Now, calculate a time. Seems to be very calculator heavy at this point, this exam. At least the section B is. So 10 times 2e negative 2 times 1.6e negative 3 over 0.5. Okay, 6.4 times 10 to the negative 4 volts. Okay. Let's check our answers. Here we go. Correct answer. It's a very standard question. Most common error was to calculate the correct change in flux over time, but not to multiply by 10. So you always need to double check. Is it a single loop? Is it multiple loops stacked together? That's what the turns tells us. Okay, and that's our N. Okay, question 2b. Sketch the EMF induced in the loop as it passes into, through, and out of the magnetic field. You do not need to include values on the axes. Okay, so we're required to make an EMF graph. The easiest way to do this is to create a flux graph first in pencil. Okay, so let's think about what the flux is doing at the different stages of this loop's motion through the field. Okay, so it's going to go like this. Okay. So when it's outside the field, so remember this, we're doing flux, I'll do it in red. Okay, and you would do this in pencil and then rub it out later. So when the loop's outside the field, the flux is 0. Okay? Because it's a square loop, when it's entering the field, okay, the amount of loop in the field sort of increases at a linear rate. So the flux is going to increase to some maximum there. So at this point, now the loop is completely inside the field. As the loop is traveling through the field, the flux is not changing. Okay, it's a maximum flux, but it's not changing. So it's a straight line across. Then when it starts to leave the field, the flux will decrease at a linear rate. And then when the loop's outside the field again, the flux is 0. Okay. Now we're going to draw our EMF graph based on what we've got here. So remember, your EMF graph is equal to the gradient of the flux graph. Okay, it's the rate of change of flux. So we just look at what the gradient is doing at these stages. Okay, so right now outside the loop, the gradient is 0. So the y value of the EMF is 0. Okay, so that would be that. Okay. Oh, disappeared. It's going to be like that. What's the next part of the graph doing? So the graph's a positive value. Okay. So we can just jump straight up to a positive. Sorry, the gradient's a positive value. So the y value, the EMF, will be a positive number. Technically it should be negative, but because there's no indication of which direction around the loop is positive or negative, we're free to choose. Okay, so I'm going to just say, just follow what the gradient's doing. So constant gradient means a constant y value for your EMF. And that jumps straight up like that. And we can delete this. Here, the gradient of your flux graph is 0, so the y value of your EMF graph is 0. So it's a straight line across at the bottom there. Here, the gradient is negative for your flux graph, so the y value is negative, okay, whatever that gradient is. So it jumps down to here and goes across like this. You can delete that part. And then again, when it's outside the loop, the flux is 0, so the EMF is 0. Or I should say the gradient of the flux is 0, so the EMF is also 0. So your graph is going to look something like this. Now, it's not wrong to flip this around about the time axis, but that's good enough. Okay, so let's check the exam report for common mistakes. Okay, so there you see the graph matches ours. Good. An inverted version of the graph was acceptable, so that's what I was saying. So there's no indication of which direction is the positive direction in this loop, so there's no indication of whether like the positive voltage is. So you're free to choose. The question was not answered well, with most common error being to draw the flux graph. Okay, so just be careful. Okay, the flux graph is handy. Okay, it's used as like a stepping stone to be able to draw the EMF graph, but they're different. Okay, flux is different to EMF. All right. Yeah, so have a read of that there. Let's keep going. Question 3. Students build a model of a simple DC motor as shown in figure 3. So it's a motor, which means it uses electricity to turn. It doesn't create electricity by turning. Okay, so it's not a generator. The motor is set with a coil horizontal as shown. The power source is applied. Will the motor rotate in a clockwise or anti-clockwise direction? Explain your answer. Okay, so let's look at the battery here. So the current is going to come out of the positive side into this commutator, and it's going to go through the loop that way. Okay, and it's going to go around that way initially. Okay, the magnetic field that the loop is in is going out of north into south like that. Okay, so let's focus on the side EF. Okay, just focus on the side of the coil EF. So there's a current that is perpendicular to the magnetic field. Therefore, the magnetic field will apply a force on that current. And the direction of that force is determined by your right hand slap rule, or the right hand palm rule. So here's what we do. We get your right hand in front of you. Your thumb is going to point in the direction of the current. Okay, so that's sort of out of the page for us here. Okay. Your fingers are going to point in the direction of the field lines, so your thumb's pointing out of the page towards your face. Your fingers are going to you're going to curl your hand around as best you can, so your fingers point to the right. Which way is your palm pointing? It's pointing upwards. Okay, it should be, unless you've got some weird alien hand. Okay, so the force on this side of the coil is going to be upwards. You could do a similar analysis on the side GH, and you'll see that the force on that side will point downwards. So in this case, the coil is going to rotate clockwise. Okay. Now to explain our answer, we just explain what I just said. So on side EF, from the right hand slap rule, the magnetic force is downwards. Okay, and that's what causes it to, oh sorry, I said downwards, it's like upwards. Silly me. Upwards. Okay, and that's what causes it to rotate clockwise. Let's double check your report. Where's my mouse? Okay, so here it is. Answer is clockwise. Students were required to explain how they determined the direction. They were required to identify the direction of the current in the loop as hg or similar, then relate this to the direction of rotation. The most appropriate way to do this was to refer to the right hand rule or similar. Okay, so yeah, there you go. I guess, you know, it is 3 marks, so there does need to be an indication that you know what direction the current is flowing, and that's done by me annotating my diagram here. So if the examiners are being nice, they'll see your annotations and they'll say, yep, you know what direction the current's flowing, and you've got the right hand rule written down here, okay, the right hand slap rule, and then you've also, yeah, you've just used it the right way, okay. If you don't have an annotation here, you might want to just place a safe bet and write down that the current in the side EF is flowing, I guess, from F to E, if it's not clear from your own annotations here, okay, and that should get you the full marks. Okay, question 3b. One student suggests that slip rings would make it easier to make, would be easier to make than a commutator, and that they should use slip rings instead. Explain the effect that replacing the commutator with slip rings would have on the operation of the motor if no other change was made. Okay, so the whole point of why a commutator is used in the first place for a motor is that when the coil reaches like a vertical position, so the coil is like that now instead of how it was to begin with, what happens there is the current sort of switches off for a second, and the rotation swings the coil around, and then the opposite commutator is connected to the other side of the battery, and so the current basically swaps its direction from, like, let's say we're talking about EF, so right now the direction is from F to E. When it reaches this vertical position, the current will switch off, the coil will swing around a little bit, and then the current will now be flowing from E to F. Now it needs to do that because the current needs to flow like into the page when it's on that side, so that the force is still downwards, and that's what causes that constant rotation. Okay, so it's the flipping of the current every time it reaches that position. Now if you used slip rings instead, the current will always be in the same direction on that side of the coil. And so what's going to happen is your coil, when it reaches this vertical position, it might swing past that position a little bit, but the force is still going to be from F to E, which means that according to our right hand slap rule, it's going to be forced upwards again, and it will just sort of reach a point where it will just stay in this vertical position and it won't rotate anymore. Okay. So if the question is explain the effect that replacing the commutator with slip rings would have on the operation of the motor, you would say the current would stop. You'd say the current would remain constant. This is how I'm going to phrase it. The current will remain constant through each side of the loop. Okay, and then the coil will stop moving as it reaches the vertical position, since the force on, say, side EF is always, well, in this case, it will always be upwards. Okay. Now let's see what the examiner report says. It's a 2-mark question, so I don't believe too much depth is required here. Where's my mouse? There it is. Okay. So students were required to identify that the motor would no longer function. That's what we've done here. The coil will stop moving. Further, they were required to point out that the loop would rotate by 1/4 of a revolution to the vertical position but would not rotate further, so we've done that. The most common errors were to provide statements regarding the purpose of slip rings and or split ring commutators, or to describe how the motor would no longer work as a generator. Okay, it's not a generator, it's a motor, so that's just a wrong thing to say. A number of students stated that the loop would rotate 180 degrees before stopping, and a few who stated that the loop would oscillate between the horizontal and vertical positions. Alright, so no. So all you had to say was, once it reaches that vertical position, it's going to stop. And the reason is because the force on side EF will be upwards. It's not going to flip around and point downwards as it passes that point. So there will not be a continuous rotation anymore. It'll just rotate up and just sort of stick there. Okay, been talking for 25 minutes. I'm going to pause, and I might have to break this video here, only because I'm going to be a bit busy. So we'll pause there. We'll see if I break it into 2 videos. But go have a break yourself, and we'll come back in a second. Okay, so let's go with question 4. Let me just get rid of this thing here. Okay, question 4. Figure 4 shows a simple AC alternator. So now this is a generator question. With the output connected to an oscilloscope and a light globe. The oscilloscope can be considered as having a very large resistance. The coil is rotated as shown in figure 4. So it's an alternator. This is a generator. So we rotate it ourselves. Okay, it doesn't use electricity to rotate. We rotate it to make electricity. Alright. So here's the output of what happens when we rotate it. Cool, so it's generating a voltage, and the voltage varies over time. Part A, the AC alternator is to be replaced with a battery. What voltage should the battery have for the light globe to light up with the same average brightness as it did with the alternator? Show you working. Okay, so this is where we now have to make the connection between AC electricity and DC. So if we go back to our graph, okay, you'll notice that there's like a peak voltage. It sort of varies over time. Okay, now if this is connected to a light globe, the light globe doesn't care whether the electricity is running one way through it or the other way. Okay, it just cares that there is electricity running through it. All right. So if we can sort of average out this, like if I flip this upwards to make it up here, and we sort of work out what the average voltage is, that's how much we need if we're going to replace it with DC. Okay. Now the way that we do that is we use what's called RMS voltage. Okay. So if we look at the peak voltage, okay, that peak voltage is about 4, and so the equivalent would be the RMS. Okay, if we're going to replace it with DC. Now the RMS voltage is the peak voltage divided by the square root of 2. So the peak voltage is 4 volts divided by the square root of 2. Quick calculation here. Let's get my calculator. Alright, so 4 divided by root 2, 2.8. So 2.8 volts are required for us to be able to replace this AC generator with a battery. Let's just quickly double check the exam report. Yep, 2.8. The 2 most common errors were to multiply the peak voltage by root 2 or to simply state the peak voltage. Yeah. So just remember to make that connection. Okay, the RMS voltage is the DC equivalent that would deliver the same amount of electrical power. All right. So that was 2.8. Part B, the rate of rotation of the loop is doubled, so that means it's spinning faster, twice as fast as before. On figure 6, sketch the output that will now be seen on the oscilloscope. The original waveform is shown as a dashed line on figure 6. Okay, so what's going to happen here? Let's have a think. The rate of rotation is doubled, which means it completes a rotation in half the time that it did before. Yeah. Now your EMF, your average EMF, well, you don't even have to worry about the average. We'll just look at how it's related to this equation. So the change in flux over the change in time. Okay, actually I might even just say it's proportional to 1 over the change in time. Now what's the change in time? That's like, just think of that as like the period. Okay, for an alternating generator like this, delta t, just think of it as the period. Okay, for this particular question, for this purpose. If we double the rate of rotation, the period halves. Okay, that's what I was saying before. You're spinning it twice as fast. It takes half the time to complete a rotation, right? So everything's happening twice as fast, so it takes half the time to complete the rotation. So if I halve that quantity in the denominator there, overall my voltage will double, won't it? Okay, that's that proportionality showing its face. Not only that, so what I can expect to see is my peak value is going to be at 8 and negative 8. Okay, but because I'm changing the rate of rotation, the period halves, and so the peaks, everything gets sort of squashed by a factor of half, right? So all the peaks, where they lie on the horizontal axis, they're going to half. So that peak will shift to here, that peak will shift to here. No, it won't, will it? Yes, it will. So everything. Let me restate that. Every critical feature of this graph basically halves its distance from where it actually is. So this peak is going to go to here. Now the peak is 2 units away from where it crosses the x-axis. So now it's only going to be 1 unit away from where it crosses the x-axis. So it's going to look like this. I should say the peak is up here actually. So it's going to look like this. It's going to go up, then it's going to go down through there. So everything's happening at 1 division of the time axis now. Okay, everything gets squashed by a factor of half. So it's going to go down there like that, and then it's going to go up there like that. I don't know how many we have to draw on here. It doesn't say, so we'll just draw as many as we can. So again, 1 there, 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 1 there. Oh geez, how much do I have to do? Okay, there we go. So that's what's going to happen to our graph. So 2 things: the voltage doubles because by halving the time it takes for it to rotate, the voltage doubles. That's just due to the proportionality. And because we're changing the time it takes to rotate, the period itself changes to half of what it originally was. Okay, let's just double check the report. Yep, there you go. Everything gets squashed by a factor of a half, and the voltage doubles in its peak. The most common, don't look at that. The most common error was to double the period but not the amplitude. Okay, so you do have to remember that voltage in an alternating graph, in an alternating generator, does rely on how fast it's going. Okay, so the speed of its rotation, or the period, depending how you look at it, will change what the voltage output is. Okay, question 5. Our physics class is investigating power loss in transmission lines. The students construct a model of a transmission system. They set up the model as shown in figure 7. The model consists of a variable voltage AC power supply, 2 transmission lines, each of 4 ohms, total resistance 8 ohms, a variable ratio transformer, a light globe, and meters as needed. Oh, that's a big sentence. The purpose of the model is to operate the 4-volt light globe. The variable ratio transformer is one in which the ratio of turns in primary windings to turns in secondary windings can be varied. The resistance of the connecting wires can be ignored. Okay, so it's a pretty standard transmission system. So you get your voltage supply here connected to transmission lines with a resistance, and then there's a step down transformer over here, it looks like, and that's connected to the load. In their first experiment, the transformer is set at a ratio of 4 to 1, and the current in the transmission lines is measured to be 3 amps. The light globe is operating correctly with 4 volts across it. Calculate the power dissipated in the light globe. Show your working. Okay, so the light globe's over here. Okay, there is a current of 3 amps at the moment over here, and the ratio of the transformer is 4 to 1, which means the current on the other side of the transformer, according to your transformer equation, okay, I2 over I1 is equal to N1 over N2, so I2 is equal to I1 N1 over N2, which is 3 times 4 over 1, 12. And so the power that's dissipated is, well, we know that there's 4 volts across that light globe, so it's voltage times current, which is 4 volts times 12, which is 48 watts. Okay, let's double check. I haven't made a critical error somewhere. This mouse is annoying. Yep, 48 watts. The most common error was to calculate the power using the current in the transmission lines as the current through the globe. Yeah, so you had to have transformed that current because it is going through a transformer. Another common error was to calculate the current through the globe as 1/4 of the transmission line current. So that's using your transformer equation wrong. Yeah, so this just shows that a lot of people don't really know what's going on in this setup. So you be one of the people who do know what's going on in the setup. Alright. 5b. It is 5, isn't it? 5b. Calculate the voltage output of the power supply. Show you're working. So what is the voltage of the power supply? Well, let's think about this. We know how much power is being used by the globe. Okay. Actually, do I even need to worry about that? Probably not. Let me have a think here. So the voltage output of the power supply. Okay. Well, okay. I think we're going to do it like this. Okay, I'm going to set it up like this. I'm going to do what I was about to do, which makes the most sense to me. Alright, so we've got a current in the transmission lines, and we know the total resistance of the transmission lines is 8 ohms. Okay, so we can actually work out the power lost in the transmission lines. So the power loss in the transmission lines is I squared R, which is 3 squared times 8, which is 72 watts. Okay, so 72 watts of power is used up just by transmitting over these lines, which means we've got some power left over going into the transformer and then being used up by the globe, which we've already worked out here to be 48. Okay, so 48 of watts of power being used here, 72 watts of power have been used here, and so the total amount that's actually been generated over here is just the sum of those two. So then 72 plus what we've already worked out to be 48, that's 120. Okay, now the question is not what is the wattage, what is the power of the power supply. The question is what is the voltage. Okay, but now I know what the current is in the transmission lines over here. That's the same current as what's coming out of the power supply. So voltage is just power over current, which is 120 over 3, which is 40 volts. Now to me that makes the most sense. I'm sure there's another way to do it, so let's have a look at your examiner's report. Okay, so the examiner's report says the voltage drop across the transmission lines is that. Okay, V equals IR, that's just your Ohm's law, because we know what the current is, we know the total resistance of that. Sure, that makes sense, 24 volts. The input voltage to the transformer is 4 times the globe voltage. And that's, yeah, okay, yep, so what they're doing is they're saying we know there's 4 volts on this side of the transformer, the ratio of the transformer is 4 to 1, so there must be 16 volts going into the transformer, and then the 24 volts that have been, I guess, used up here, plus the 16 volts going into here means that the voltage coming out of this is 16 plus 24, which is 40. Cool, yeah, that makes sense. Alright, it just didn't come to me at first to do it that way, but perfectly fine way to do it. It does say a number of students use an alternative method. In this case, they use the 48 watts, so this is the way that I did it. And that got you the same answer, so that was fine. The most common error was to use 4 ohms for the resistance, so just make sure that you're using the total resistance of the transmission lines. And yeah, that seems to be it. Alright, there's one more for question 5. Oh my god, 5. C, D, E. Alright, let's quickly get through those. Calculate the total power loss in the transmission lines. Well, we've already done that. Okay, that was up here, 72, so just copy that down. So P loss equals I squared R equals 3 squared times 8 equals 72. Okay, so that's fine. We already know that that's what the answer is. In a second experiment, the students set up the variable ratio of the transformer at 8 to 1 and adjust the variable voltage supply so that the light globe operates correctly with 4 volts across it. Calculate the total power loss in the transmission lines in the second experiment. Show you working. Okay, I'm actually going to pause here because I have to go and run. I'll come back. It's just going to be pause. We won't stop the video. I'll just be back in a second. Alright, so 5D, in a second experiment, the student set the variable ratio of the transformer at 8 to 1 and adjust the variable voltage power supply so that the light globe operates correctly with 4 volts across it. Calculate the total power loss in the transmission lines in this second experiment. Show you working. Okay, so to me, when it says operates correctly, that means it's still operating with the same values as it did before. 4 volts, but there's also going to be 12 amps going through it. Okay. Operating correctly means it uses the same voltage and current as it always does. So we can assume here that the current going through on the globe side, so I'll call it I2, is equal to 12. So if we want to work out the power loss in the transmission lines, we need to know the current in the transmission lines, and that's going to be different now because the transformer is different. Now according to your transformer equation, I1 is equal to, let's do this, it's going to be I2 over I2 times N2 over N1, I think. Yes, and that is 12 times 1 over 8, because that's what the ratio is. Alright, 12 times 1 over 8, 12 over 8 is, oh, come on, Adam, you can do that in your head. 12 times 8, 12 times 8, 12 over 8. 1.5, of course it is. 1.5 amps in the transmission lines, and therefore the power loss, assuming that the resistance hasn't changed, is I squared R, 1.5 squared times 8 ohms. 1.5 is 2.25 times 8. That's going to be 2468. That's going to be 9. Am I right? Let's double check. 1.5 squared times 8. Come on, give me 9. No, I was wrong. What am I doing? 2 times 8 is 16, you numbskull. That's why you don't do things in your head. Alright, but there you go. Double check the exam report. Yep, 18 watts. Very good. Alright, last one. Suggest 2 reasons why high voltages are often used for the transmission of electric power over long distances. Okay, well, high voltage, I guess, is able to be, well, if you want to generate the same amount of power, so for generating the same amount of power, high voltage is equal to low current, okay? And low current is good because it minimizes power loss due to your power loss formula. Okay. 2 reasons why high voltages are often used. I can't even think of what the second reason would be. I mean, that's a pretty good reason by itself. Let's just have a look at the examiner's report, what they're expecting to see. Okay, so a number of responses were accepted, including but not limited to reducing transmission current, so that's what we've got. Reducing power loss, well, we've got both of them, so I guess we get 2 marks for that. Common error was to state one of the factors above and explain that action in detail. While the response was often correct, the question required 2 reasons. Well, for me, to me, this seems like one reason. It's you want to minimize power loss, And that comes from having low current. That's just one reason. Okay, you have a high voltage to make low current, which minimizes power loss. That's a single reason, but according to them, it's two reasons. So I don't know, the wording of that question sounds a bit dodgy, but it is what it is. It looks like we've got 2 marks for that, so there we go. Alright. Question 6. A ball of mass 2 kilograms is dropped from a height of 2 meters above a spring as shown in figure 8. Cool. The spring has an uncompressed length of 2 meters. The ball and the spring come to rest when they are at a distance of 0.5 meters below the uncompressed position of the spring. Okay, so let's just understand that. So there's a spring, it is unstretched at the moment. Ball starts up here, ball falls, ball hits the spring, compresses the spring, and then the ball sort of, I guess, come to rest here. Now I'm guessing that means they've momentarily come to rest before the spring then like pops the ball back up. Yeah, so that's what's happening here. Alright, part A. Using G equals 9.8, show that the spring constant K is equal to 392 newtons per meter. Show you're working. Alright, I think the best thing that we're going to do here is use conservation of energy. So let's think about the energy interactions that are taking place here. So the ball falls a distance of 2.5 meters. Yes, it falls 2 meters to get in contact with the spring, but then it still falls another half a meter. Like, it loses that much height. So in total, it loses 2.5 meters of height. So it's losing gravitational potential energy. Now the ball, we're assuming, is started at rest, and then it's dropped. So it's got 0 kinetic energy at the top. When it reaches this position, it still has 0 kinetic energy, right? But now the spring has been compressed, and so the whole system has now gained spring potential energy, has to have gained it from somewhere, and it looks like it's probably gained it from the loss in gravitational potential energy. So we can set that up with an equation as follows. So mg delta h is equal to half k delta x squared, and our job is to show that k equals 392. So let's solve for k. K equals, and just do some algebra here, so it's going to be 2mg delta h over delta x squared, and let's just sub in our numbers. So 2 times the mass of the ball, so 2 times 2 kilos, times g, 9.8, times the change in height of the ball, which is 2.5 meters, over delta x squared. So delta x is how much the spring compresses by. So it compresses by 0.5 meters. So that's 0.5 squared. Alright, now hopefully we get the right number here. Let's have a look. Right, so 2 times 2 times 9.8 times 2.5 over 0.5 squared. Fingers crossed. Yay! Cool. There we go. Part B. Determine the acceleration of the ball when it reaches its maximum speed. Explain your answer. Alright. So let's think about this. When is the maximum speed of the ball going to be reached? So what's happening to the ball here? Well, it gets released and it accelerates downwards, obviously. Okay, that's because of gravity, right? And it keeps accelerating until it hits the spring, alright? And what's going to happen is, as it starts to compress the spring, so let's zoom in here, alright? Here's the spring. Alright, here's the ball just hitting the spring. There's going to be a point somewhere, so I'll draw the compressed spring. So that's the fully compressed spring. Obviously the ball is moving at this point, downwards. Here the ball is not moving, okay? So the ball is eventually going to start to slow down, okay? The point at which it starts to slow down is when the upwards force of the spring is larger. Actually, I'll draw that a bit different. So when the upwards force of the spring, so the spring is supplying an upwards force on the ball, and that upwards force has to be larger than the gravitational force that's acting on the ball. Okay, when that starts to happen, the ball will slow down. Okay, and when those two forces are equal, that's when the ball's acceleration becomes zero. But prior to that moment, the ball is always accelerating downwards because gravity is stronger than any upwards force that happens to be applied on the ball. So the maximum the maximum speed of the ball occurs when the acceleration is zero, right? So that's our answer. So to determine the acceleration of the ball when it reaches its maximum speed, I'm going to claim that that's zero, okay? Because the ball continues to accelerate down until F net equals zero, and therefore acceleration equals zero. All right, let's double check our exam report. There you go. So when the ball reaches its maximum velocity, the acceleration will be zero. This will occur when the net force on the ball is zero, or when the gravitational force is equal to the upward spring force. That's exactly what we stated. Okay, so I hope you can understand the reasoning behind this. So the ball accelerates down when you let it go. It gets into contact with the spring, and then the spring will begin to apply an upwards force. Gravity is always the same strength pulling it downwards, so the gravitational force is always the same length vector. But the more you compress the spring, the larger the spring force vector becomes. And at the point where they balance each other out, that's when the ball will have its maximum speed. Again, because prior to that, the gravitational force is always larger than that spring force. And so the net force is still downwards, it's still accelerating the ball up until that point when the forces are equal. Okay? Part C. Calculate the compression of the spring when the ball reaches its maximum speed. Show your working. Okay. So, how are we going to do this? Okay, well, I mean, the hint is from the answer that we just provided. So, the maximum speed occurs when the acceleration is zero. And so, the acceleration is zero when the gravitational force is equal in magnitude to the upward spring force. I don't need a delta x. I don't need a bracket there. Okay. Now, our job is to work out at what compression, at what delta x does this occur. So we're just solving for delta x. Yeah. So delta x equals mg. Okay. M was 2. Yep, 2 kilograms. G is 9.8. K, we've been told, is 392 from up here. And so we calculate that. Alright, 2 times 9.8 over 392, 0.05 meters, or 5 centimeters. Okay, that's not the same as what it's compressed by. It's compressed by 50 centimeters, so those are two different numbers. So let's check our exam report. Yep, so again, acceleration, so maximum speed occurs when acceleration is zero. Acceleration is zero when the two forces, gravitational force and the upward spring force, are equal in magnitude, so they cancel each other out. And then we solve for x. There you go. So overall, it appears this question wasn't answered very well. So you can see in part A, almost 50% got nothing. Part B, 80% got nothing. And part C, 86% got nothing. So that's a really poorly done question. And that just shows that, these kinds of energy interactions are sometimes really hard to to analyze. Okay, but you just need to be really careful. Okay, make sure you understand what interactions are taking place. And I think that the hard part was this question, because question part C basically relied on you being able to know the answer to part B. So if you didn't get B, then C was probably, completely out of ballpark. So yeah, make sure you review these kinds of questions. Okay, question 7. We've been recording for 55 minutes, so I'm going to make this the last question for this video. Question 7. A small ball of mass 0.2 kilograms rolls on a horizontal table at 3 meters per second, as shown in figure 9. Yep. The ball hits the floor 0.4 seconds after rolling off the edge of the table. The radius of the ball may be ignored. In this question, take the value of g to be 10. That's nice. They're giving us a nice round number for g. Alright, part A. Calculate the horizontal distance from the right-hand edge of the table to the point where the ball hits the floor. So the ball's going to go whee, alright, and hit the floor there. It's going to take 0.4 seconds to do that. Our job is to work out what is that distance. Okay. How are we going to do that? Well, we can just use the fact that it's traveling horizontally at 3 meters per second, and it takes 0.4 seconds to travel that distance. So this is just a speed, distance, time question. So our goal is to work out distance. So distance equals speed times time. If you forget, you've got your triangle, distance, speed, time. Okay. So speed is 3 meters per second, time is 0.4, 3 times 0.4 is going to be, I can't do this in my head because I'm lazy, 3 times 0.4, it's going to be 1.2, sorry, yeah, 1.2. So it travels 1.2 meters horizontally in that time. Part B, calculate the height of the table. Alright, so we know how long it takes to fall. So what we're going to do is use vertical components of motion to work out the height of the table, because the height of the table is a vertical thing, right? So let's write down what we know about its vertical motion. So its starting vertical speed is 0, because it's rolling horizontally at the initial stages. Vertical acceleration is negative 9.8, that's gravity pulling it downwards. The time it takes for it to travel that distance vertically was 0.4 seconds, and our job is to work out basically how far it travels vertically. Okay, so your displacement. So we've got u, a, t, we want s, so our equation is s equals ut plus half at squared. The at goes away because, the ut goes away because u is 0, and this now becomes half times negative 9.8 times 0.4 squared. That equals, calculator time, it is 0.5, so that's the half, times negative 9.8 times 0.4 squared. Okay, so because it's negative, that's just telling me the ball is falling. So if we ignore the negative, that's the height of the table. So 0.784, also 0.78 meters. Okay, at this point we'll check our exam report. Okay, so question A, like I said, speed equals distance over time. Pretty well answered that one, so almost 80% got it right. The next one was using the Suvat equations, exactly what we did. They've just done it to one significant figure. Otherwise, oh, hang on, no, I've screwed up because I didn't use g equals 10, and that's why we highlight, isn't it, everyone? Okay, so replace some things here. So that's negative 10. That is also negative 10. And now that changes our answer to something else. Is it 0.8 exactly, or is it not? I don't know. Let's work it out. So hang on. It's going to be 5 times 0.16. 5 times 16 is 80, so yeah, it's equal to 0.8. Exactly. Cool. Part C, calculate the speed at which the ball hits the floor, show you're working. Okay, now we've got to be careful here because it's hitting the floor at an angle. It's hitting the floor like that, okay? So it has both a horizontal component, which we'll call Vx, and a vertical component, which we'll call Vy. And the vector sum of those components will give us our speed that it hits the floor at. So we've got two things to work out. What is the horizontal speed at which it hits the floor, and what is the vertical speed at which it hits the floor? Then we do some Pythagoras, okay? Now the horizontal speed is pretty easy because it's constant throughout the motion of the ball. It's going to be 3 meters per second, so we can make a note of that. So Vx equals 3. Now we've got to work out Vy. So Vy is what we want. What else do we know about the ball? Well, we know that its acceleration is negative 9.8. We're talking vertically here. Starting velocity is 0, and the time taken to hit the floor is given to us as 0.4. Now, so we could use also the height of the table, but the height of the table is a derived quantity. Yes, it is an exact number, but I prefer to use numbers that are given to us. Yeah. There's no reason why you can't use the height of the table, but it hinges on the fact that you got it right to begin with. So that's why I'm not using it. We're using values that we definitely know are true. So we've got VAUT, so the kinematic equation for that is V equals U plus AT, right? So V equals U plus AT, and so the final vertical speed of the ball is 0 plus negative 9.8 times 0.4, which is, just make a note, this is vertical speed. So 9.8 times 0.4, negative 3.92. Cool, so negative just tells me it's going downwards. Right, last step is to combine those two values vectorially. So the final speed is the square root of the sum of their squares, so 3 squared for the horizontal speed, plus, you can ignore the negative here because we're squaring it, so 3.92 squared for the vertical speed, and that gives us a final answer of square root of 9 plus 3.92 squared. So that 9 is just the 3 squared. 4.94, let's say, meters per second. 4.94 is our claim. Let's check the report. Yeah, they've rounded it up to 5. Yeah, they've done the... Oh, again, I've done the same mistake. This is why I hate questions like this, because you're so used to using 9.8 for the entire year that when they say to use 10, it's completely slips your mind. So that's going to be negative 4. That's going to change to 4. 3 squared plus 4 squared is 5 squared. So the square root of that is 5. There you go. Alright. So don't do what I do. Make sure you actually read the question, highlight that, and if it says that, smack yourself in the face a few times so that every time you think about acceleration due to gravity, you'll be reminded of the pain, and then you will probably not make that mistake. Okay, I'm going to cut the video here. We're going to have part 3 with the continuation of section B in the next one.